Hello, so this is going to be a combined science trilogy past paper walkthrough for Physics Paper 1 Foundation tier, and this was the paper that was sat in June 2022. Okay, so I'm going to go through it, model it, how I would have tackled it, and I've put links at the bottom to the different topics if you need to go back and revise that topic. So, question number 1 then. A student investigated how the potential difference across a filament lamp affects the current in the lamp, and this is the circuit the student used. Question 1.1. Figure 2 shows a circuit symbol. What component does this symbol represent? So it's either an ammeter, a battery, a lamp, or a variable resistor. Well, we should know an ammeter is just a circle with an A. A battery is actually the one that is above, but just making sure we know them. A lamp is just a circle with an X, and a variable resistor. All resistors are a rectangular shape, and a variable resistor just has an arrow going through it. Which component in figure 1 did the student use to adjust the potential difference across the lamp? So the potential difference comes from the battery, so you can put the battery or the cell, okay, that is actually allowed, but the key device that can adjust the potential difference is this one here, which is the variable resistor, okay? Because if you vary the resistance, you'll vary the potential difference. So variable resistor. When the voltmeter was not connected to the circuit, it gave a reading of 0.4 volts. How could the student correct all the readings taken from the voltmeter? So they've had the voltmeter on, even when it's not connected, so it's a zero error. Even when it's not connected, it's still got a reading of 0.4 volts. So it's not been reset to 0. So therefore, when they plug it in, every reading is going to be 0.4 higher than actually it is. So what should they do in order to get rid of this plus 0.4 reading? Well, you do the opposite, which is just simply subtract 0.4 from everything. And that would reset it back to the real value. The student recorded the results, or 3 values for each potential difference, and it shows the results for 2.5 volts. It says calculate the mean current in the lamp. We can see the 3 tests here, and because they're all quite similar, there's no anomalies in it, and this is just calculating a mean. You should know a mean, you add them all up, or how many you've got. So 0.54 plus 0.58 plus 0.53. I'm confident there's no anomalies, so I just leave it like that, and I divide by how many there are, which would give me a mean of 0.55. It then says calculate the power of the lamp when the potential difference across the lamp was 4.8 volts and the current was 0.75 amps. So power is potential difference times by current. So you've got your equation already written out. You substitute in your values. So potential difference is measured in voltage, and then current is 0.75. So you're just timesing those two numbers together, and that gives me a power of 3.6 watts. And the units are already given to you. So a nice easy one there. It then says calculate the resistance of the lamp when the potential difference across the lamp was 4.8 volts. The current in the lamp was 0.75. So again, you're calculating resistance and it's given you the equation. So substitute in your values. Potential difference is voltage, so that is 4.8. Your current is 0.75. So 4.8 divided by 0.75 this time, as per the equation, gives you a resistance of 6.4 ohms, and that's given to you already. So we then need to complete the sentences using the words in the box. Increasing the current in a filament lamp makes the temperature of the lamp blank and the resistance of the lamp blank. Well, if you've got more current flowing through a light bulb, what happens to the light bulb in terms of its temperature? It will get hotter. So it will just be increases. And the resistance of the lamp blank. Well, if you've got the increasing temperature, that means that actually you've got more current flowing through that bit of wire, and therefore it's going to be colliding with more atoms, and this actually causes the resistance to increase, because it's the electrons colliding with the atoms in that metal wire that generates that light and heat. So it would also be increase. Question 1.8. Which graph shows the relationship between the potential difference in current for a filament lamp? These are three little voltage current graphs that you need to know. This is the shape for a filament lamp, okay, because it curves, because it's affected by temperature, because lamps get hot, so you don't get a perfect straight line. If you get a perfect straight line, that means it is a fixed resistor, because they're not affected by temperature. And the last one that goes flat and shoots up is a diode. Okay, diodes are basically, think of it as being like a roadblock. They've got really high resistance in one direction, but a low resistance in the other one. You've got to know it goes straight and then shoots up. Right, question 2 then. Figure 3 shows a lift near the bottom of a building. The lift is attached to a cable to a counterweight. The electric motor moves up the lift. The lift is moving up. So you've got the counterweight going over a pulley. Okay, we know the lift is moving up. Okay, question is, as the lift moves up, how far does the counterweight move down? Does it move a shorter distance than the lift, the same distance, or a longer distance? Well, we see here, the counterweight and the lift, they're connected by a cable. And just because that they might be different sizes, that cable is always connected. So therefore, if the counterweight goes down a certain amount, the lift would go up by a certain amount. So the distance would always be the same. So it's the same distance as the lift. Question 2.2. What happens to the gravitational potential energy of the counterweight as it moves down? So the gravitational potential energy of an object as it goes down, well, if you think about when objects have the most GPE, if an object is higher up, it has more GPE. So if it's going down, it's losing its GPE, it's not being held high against gravity, and therefore it would be decreasing. Question 2.3. Calculate the change in the gravitational potential energy in the lift when it moves up 4 meters. It tells you the mass is 1300 kilograms, and it tells you the gravitational field strength on Earth is 9.8. It gives you the equation, so again, literally, you are just substituting in what you've been given. Your mass is 4, your gravitational field strength from the question is 9.8, and your height is 4, your mass from the question was 1300 kilograms. So 1300 times by 9.8 times by 4 gives you an answer of 50,960. Just put it in your calculator, and again the units of energy are given to you. So that's a relatively easy 2 marker. Question 2.4 then. Choose answers from the box, and this is about energy transfers. So friction between the brakes and the cable caused the speed of the lift to decrease. As the speed decreases, there is a decrease in the blank energy of the lift. And we're talking about the speed of the lift, so therefore it's about movement. If you've got less movement, you'd therefore have less kinetic energy, because that is your movement energy. As the speed decreases, there would be an increase in the blank energy of the brakes. Okay, well, at the brakes, as they're going up, or they're pulling the lift up, what happens to a brake? Well, it heats up. So we're looking for something that is relating to heat energy. It's not chemical, it's not elastic potential, it's not going up high, it's not kinetic. So therefore, you might be thinking, it would be thermal, but that's not an option. So therefore, the one that makes most sense out of the objects given to you is the internal energy. Basically, the brakes, that thermal energy is going to the internal store of the brakes. The motor transfers different amounts of energy each time people use the lift. Which factors affect the amount of energy transferred by the motor as the lift moves? Okay, so we're looking for what factors would affect the amount of energy used by the motor. So what would make it work harder or less hard? Is it going to be the distance? Well, if the lift is moving a greater distance, odds are more energy is being used. That's why I would be saying that. Does the height of the building itself actually affect how much energy is being transferred? Probably not. The length of the steel cable, well, that's consistent all of the time, so probably not. The maximum power of the motor, well, the motor doesn't work at its maximum power all of the time, so that wouldn't necessarily always affect it. But the other key thing would be the weight of the people in the lift. If you've got a heavier object, or if you've got more people in the lift, that motor is going to be working harder and transferring more energy in order to move them. So it'd be the top and bottom one. Question 2.6. The weight of the lift and the counterweight stretch the cable by 0.015 metres. The cable acts like a spring with a spring constant of 880,000 Newton metres. Calculate the elastic potential energy of the stretch cable, and it gives you the equation to use. So again, you just take the numbers, you're working out elastic potential energy, so there's no rearranging needed. So the spring constant is 0.5 times by the spring constant, which was 880,000, times by the extension squared, which is 0.015. Okay, so what you then need to do is make sure that the 0.015 is squared just by itself. You don't square the whole thing, so it might be worth just doing the squaring part first and then timesing it all together. And if you do it correctly, it should give you an answer of 99 joules. But if you get a different number, odds are you've not put the brackets or the square in the right place and you've squared the whole answer. If you get it wrong on your calculator, but you've written it out like this, you would still get 1 mark for showing that you've actually know what to do. You've just made a mistake on your calculator. Question 2.7 then. A lift system using a counterweight is more efficient than a lift system that does not use a counterweight. How does having a more efficient system affect the energy transferred by the motor? Less energy is transferred, the same amount of energy is transferred, or more energy is transferred? Well, if I've got a more efficient system, so it's basically all of the energy that is going into it, very little amount is being wasted, that means less energy in total would be going in because less energy itself is therefore wasted. So it should just be the top one. Question number 3 then. A teacher demonstrated that the radioactive isotope americium-241 emits alpha particles. Figure 4 shows the equipment used. So you have your radioactive source, you have your count rate meter, and your radiation detector. An americium-241 nucleus emits an alpha particle and turns into a neptunium nucleus. What is the correct equation for this decay? Well, we need to know that an alpha particle, consists of 2 protons and 2 neutrons. So it has a proton number of 2 and a mass number of 4. If I was going to draw it out, an alpha particle would look like this. 2 protons and 2 neutrons are being shot out of the nucleus. So what we're looking for is our bottom number to have decreased by 2, and our top number, because it's lost 2 protons and 2 neutrons, to have gone down by 4. Now, an alpha particle, we should also say, is the same as a helium nucleus. Okay, so actually, they're all 2-4, so that doesn't help us. We're just looking at the correct numbers. I can see on my first one, actually, this one's decreased by 4, and this one's decreased by 2. So I think it's going to be that one, but then I'll just check it. The next one, well, that's going up by 4, so that one's not correct. And the next one, the bottom one's gone up by 2, so that one's not correct. So it would just be the top one. What is the furthest distance that alpha radiation can travel in air? Well, what you should remember about alpha particles is that they're generally, compared to beta particles, which is just a high energy electron, and gamma, which is a wave, alpha is the largest. Okay, so alpha is the largest of your types of radiations. Because it is the largest, it doesn't travel very far, but it can go further than a couple of millimeters. So it should just be a couple of centimeters. Question 3.3. A teacher placed a piece of paper between americium-241 and the radiation detector. The reading on the count meter decreased by a large amount. Why does the decreased reading show that americium-241 emits alpha radiation? Well, what's happening to it, if I've got my radioactive source and it's shooting out radiation, and I put a piece of paper in front of it, and I've got my detector over here, and only a couple of pieces of radiation are therefore passing through, it's showing that the paper is stopping the alpha radiation. So it's effectively blocking it. So, because, so it should just be the paper is stopping the alpha radiation. We can't say it stops all types of radiation because, yes, it's decreased by a large amount, but it hasn't stopped it entirely. And paper, you should just know, doesn't stop beta or gamma. It only stops the biggest one, that is alpha. A teacher replaced the americium-241 with a source of beta radiation, which symbol represents a beta particle, or beta particles are high energy electrons. Okay, and you just need to know that electrons have no mass and they are negatively charged. But you've got to make sure the no mass is our top number. So it would be one of these that have 0, but because it's got negative charge, it would just be the top one. So your negative charge goes at the bottom and the mass of 0 of the electron goes at the top. The count rate from the source was 119 plus or minus 7 counts per second. Calculate the smallest count rate that this could have been. So this is the uncertainty. So it's 119 plus or minus 7. So to calculate the smallest one, it's just 119 minus 7, which is 112. It's only a 1 marker, a nice simple question. A student investigated how the distance between a radioactive source and the detector affects the count rate. Draw one line from each type of variable to the description. So we should remember, independent is what I change, dependent is what I measure, controls are what I keep the same. So, using the sentence they've told us, a student investigated how the distance between a radioactive source, so they're changing the distance, so my independent variable is the distance. The dependent variable, what are they actually measuring from the statement they've given us, how it affects the count rate. So my dependent variable would be the count rate. My control variable, well, what I would then have to do is make sure what source or what control variable is actually going to affect it the most. Where if I'm changing the distance of it, odds are I would keep my radioactive source the same. Okay, because you're calculating the rate. Okay, you're not measuring the time. Right, question 3.7 then. Figure 5 shows how the count rate from the radioactive source changed with the distance. And then it is just simply, you've got the graph, and it says describe the relationship between the distance from the source and the count rate. So you've got distance from the source in centimetres and count rate per second. And you need to describe it. Describe just simply means say what you see. So you don't need to know anything for this question, it's just a scientific skill, saying what you can see on the graph. Okay, so first of all, start off with the overall pattern. As the distance increases, the count rate decreases. So as my distance is increasing, my count rate is going down. That gets you 1 mark. However, because it's a 2 marker, you need to find something else to say. And then you could probably talk about this part because it doesn't go down in an even way. It's not a perfect straight line going down. What you could then say is the biggest decreased is between 5 and 20 centimetres. And then you could also say, and track the line and follow it, you would say there's no radiation after about, well, between 40 and 50 centimetres. Okay, so literally describe questions, don't overcomplicate them, literally say what you see. Question number 4 then. Figure 6 shows a swimmer wearing a wetsuit. A wetsuit helps keep the swimmer warm. A student wrapped a thermometer in a piece of wetsuit material and placed the thermometer in water containing ice. Figure 7 shows the apparatus. So you've got the thermometer surrounded by wetsuit material and you've got some ice water around it inside a beaker. Okay? After 30 seconds in the water, the temperature of the thermometer had decreased by 7.5 degrees. Calculate the average decrease in the temperature the temperature each second. So it's the average decrease each second. So we can see you've been told it's gone down by 7.5 degrees, and that's happened over a course of 30 seconds. So you want to know how much it's gone down per second. So you would just do 7.5 divided by 30, and that gives me an answer of 0.25 degrees Celsius. So what's actually happening is the temperature is decreasing by 0.25 degrees Celsius on average each second of the experiment. The student recorded the temperature of the thermometer after 30 seconds for 4 materials. Each material was the same size and the same thickness. In each test, the starting temperature of the thermometer was 21 degrees Celsius. Table 2 shows the results. So you've got your table there, and you need to complete figure 8 using the data in table 2. You need to label the y-axis and draw the bars for materials y and z. So, again, with a graph question, take each bullet point at a time. You've got to label the y-axis. So do that part first. Don't miss that part. So you've got material at the bottom. Okay, so that one's that. So therefore, temperature in degrees Celsius must be at the side. Okay, so just through doing that, that would get you 1 mark for labelling it. And we need to draw the bars for materials y and z. So if I look at y is 16, z is 12. Okay, you can see actually they've given me a nice easy scale. Each little square is just worth 1. So y is 16, z is 12. Okay, so got 2 little squares above 10, 12. Just got to make sure it's really accurate on that. Question 4.3. Which material is the best thermal insulator? Okay, if I go back to the graph, which one is the best insulator? Well, what is actually happening is we want the temperature to stay warm. We want the thermometer to stay warm. We want to trap the heat in. So we want to go with the highest one. So the highest results, okay, we can see that Y has maintained the highest temperature for the longest time. So therefore Y is the best insulator. So Y, okay, and you would say because it showed the smallest change. Or you could put it decreased the least, okay, in degrees Celsius. The student tested a new material with a greater thermal conductivity than material Z. The piece of material was the same size and thickness as material Z. What would the temperature be after 30 seconds? Would be less than 12, exactly 12, greater than 12. As we know, material Z had decreased by 12. But if we've now got a new material and it has greater thermal conductivity, so it's a better conductor of heat, well, that means it's going to take the heat more easily. It's going to give out the heat. It's going to take the heat from the thermometer. So therefore, because it's a greater conductor, it would go down quicker. So it would be less than 12 degrees. Question 4.5. During an investigation for 0.0150 kilograms of ice melted, the temperature of the water and ice did not change. The specific latent heat of fusion of ice is 334,000 joules per kilogram. Calculate the energy needed to melt it. So again, they've been kind, they've given you the equation. You don't need to rearrange it because you're finding the energy. The mass is 0.0150. The specific latent heat is given to you, 334,000. Times those together on your calculator, and that should give you 5,010 joules. Okay, write out your equation each time so they know if you did do it wrong on your calculator, you would still get 1 mark. The student wanted to determine the density of the wetsuit material. The student measured the length of one side of a cube of the wetsuit material with a micrometer and a ruler, and table 3 shows the results. So you've got the same material they're measuring, and they've done it with a micrometer and a ruler. Okay, so you've got 3 measurements that they've done with their length. Complete the sentences. The results show that compared to the ruler, the micrometer has a higher blank. Calibration, precision, reproducibility, or resolution. Well, what we can see here is that using a ruler, you can't see any difference. But using a micrometer, you've got much more numbers of decimal places, and you can see a difference. The ability, or the smallest change that a device can measure, is called the resolution. So resolution is the smallest change a device can measure. So we would say, because the micrometer can give to more decimal places, okay, we would just say it simply has a higher resolution. Right, it then says to use the equation sheet to answer 4.7 and 4.8. Now in 2022, this was an equation that was given to students. We think at the moment it will be the same for 2024. We don't know what's going to happen in future, but this might be an equation you might need to know. Depends on what year you're sitting your GCSEs. But the equation that you would just need to look, if you do have the equation sheet, is density is mass divided by volume. Or you can write it out fully. Density is mass divided by volume. It might be on your equation sheet, or it might be one you need to know, but your teacher will tell you if you need the equation sheet. The student calculated the volume of the cube of a wetsuit material to be 0.186. It tells you the density is 0.3 grams per centimetre cubed. Calculate the mass of the cube, give your answer in grams. Okay, so we know density is mass over volume, but we've been told the density is 0.3. We want to calculate our mass, and our volume is 0.186. So we then need to rearrange the equation. To rearrange the equation to find our mass, you just do, instead of doing the 0.186 question mark divided by 0.186, you do the inverse of it. The opposite of it dividing is timesing. So 0.3 times by 0.186 equals our mass. Okay, so mass is equal to density times by volume. Then that gives us an answer on your calculator of 0.558 grams, and that would get you 3 marks. It's worth an extra third mark because you've had to rearrange the equation. Okay, so that's the end of question 4. Okay, so question number 5 then. Figure 9 shows some of the energy resources used to meet the demand for electrical power in the UK on one day in 2020. So you've got the graph here, and you've got the demand for electricity in the UK, and you've got the different sources of energy that is used to meet that demand. So gas, nuclear, wind, and coal. It then says the maximum demand for electrical power on that day was at 6 p.m. Determine the percentage of the maximum demand for electrical power that was generated using gas. So I want to know, out of the whole demand for electricity, what percentage of it was done or was resourced by gas. So if I go to 6 p.m. and I read off from my graph, I can see that the demand for electricity, if I go up, was at this point here, and reading along, that is 30,000 gigawatts. I then want to know what percentage of it is using gas, so I look at my graph, my peak of my gas at the same time, and then I've got to determine what this value is. The gap between in the 10 little squares is a gap of 5,000, and I've got 10 little squares, so each little square must then be worth 500 gigawatts. I can see I'm 3 little squares up, so from 15,000. So 15,000, 15,500, 16,000. So this point here, the peak must be 16,500. So I know that gas was 16,500 and the demand was 30,000. So, in order to put that as a percentage, you would just do 16,500 over 30,000, times it by 100 to put it into a percentage, and that should give us 55%. Okay, so remember, it's just what you got out of the total, times it by 100, and that's it. The UK government wants to reduce carbon emissions as much as possible. Which energy resources need to be used less to achieve this? So basically, which ones do we not want to use because they're putting CO2 into the atmosphere? First one, coal and gas. Well, immediately I'm thinking, yep, that sounds right, because coal is a really pollutant, really dirty fuel, and gas produces CO2 as well. They're both fossil fuels. But go through the others on the list. Gas and nuclear, or nuclear doesn't make CO2, so that can't be right. Wind doesn't make CO2, so those ones can't be right. So it has got to be the top one. A network of transformers and transmission cables transfers electrical power from power stations to customers. What is this network called? So it's basically, what is the massive network that goes from our power stations to our homes, and you've got to describe it as being the national grid. It's like the massive circuit that connects everything in the UK. Explain how using a step-up transformer makes the network more efficient. So what you should remember is that if this is your power station, it then, before it goes along all of the power lines, goes on a step-up transformer, then it goes across our country in loads of power lines, and then just before it gets to our homes, it goes through a step down transformer before that the electricity then goes into our homes. So this question is saying, why do we actually use a step-up transformer, and how does it make the national grid more efficient? And this is just a fact or some statements that you just need to know. We should know that our power lines use a very, very big potential difference. So the step-up transformer increases the potential difference in the power lines. That's why you should never go near power lines, because they've got a massive voltage, okay? Thousands of volts, okay? You don't need to know the number of it, but that's many, many thousands of volts. If you go near a power line and you get electrocuted, won't survive it. So a step-up transformer increases the potential difference. That's so all of the electricity is shot along the power lines really, really quickly and efficiently. But what this also does is decreases the current. This also decreases the current. So the number of electrons that are flowing through the wire is also less. So you've got less electrons, but they're travelling really, really fast. This reduces, or this lack of current, reduces energy loss, basically heat, to the surroundings. If you put a massive amount of current through a wire, it's a bit like what happens in a fuse. If you put too much current going through your wire, the fuse will heat up and melt. The opposite is happening here. We are reducing the current, meaning there's less electrons, so therefore there's less heat going in the wires, and therefore we're losing less energy. And that is how a step-up transformer works. A step-down transformer does the opposite. It decreases the potential difference, so we don't have thousands of volts going into our homes, and it increases the current. Right, question 6 then. A student made measurements to determine the specific heat capacity of vegetable oil. Figure 10 shows the equipment used. So you've got an electric heater connected to a joule meter. You've then got a beaker, okay, a top pan balance and a thermometer. And this question is describe how the student could use the equipment shown in figure 10 to determine the specific heat capacity of vegetable oil. Now this is probably, I think, the hardest practical in physics paper 1. You've got to describe how to use this equipment to find the specific heat capacity. You should remember the specific heat capacity of a substance is the amount of energy needed to raise 1 kilogram of a material by 1 degree Celsius. So our joule meter is obviously, the job of the joule meter is to record the energy. Our electric heater is obviously providing the heat. The beaker would be where our oil would go. We've got a top pan balance to measure the mass, and we've got a thermometer obviously to record our temperature. The equation for specific heat capacity is one that will always be on your equation sheet, which is energy equals mass times by specific heat capacity times by temperature change. Now if we rearrange that equation, specific heat capacity equals energy divided by mass times temperature change. So you can rearrange it to find the specific heat capacity. The equation will be important in the next part. So how are we going to use this equipment then? Well, to work out our specific heat capacity, we need to know the mass of the oil that we're working with. Now, it doesn't matter what mass you actually use, but I always think it's just easier to use 1 kilogram of it. Makes the calculation a little bit easier. So I would just say, point number 1, measure using the top pan balance. Use the phrases in the equipment that they've given you. 1 kilogram of oil in the beaker. So just say you get 1 kilogram of it and you've said what the equipment is used for. What you would then do, because you're going to record the temperature change, is record your starting temperature of the oil. You would then put it on the heater connected to the joule meter. Okay, so you put it on the heater connected to the joule meter. You would then, after you've got it going, leave it for a set amount of time. So let it heat for, 5 minutes. It's up to you, it's your plan. At the end, you would record the final temperature and the energy for joules that have then gone into the oil, because the joule meter will count how much heat energy, in theory, has gone into the beaker of oil that we've put on the scale. So record the final temperature and the energy. Point number 6, calculate the temperature change, okay, which would just be our final temperature minus our initial. Always say which way round it goes. And then number 7, after we've done that, we can then use our equation. So the specific heat capacity would equal our energy, which is our joule number, divided by the mass, which in our experiment was 1 kilogram, times by the temperature change. So obviously the values you can't state because you haven't got any data, but that's what you would do there in order to find it. Okay, and by setting it out like that, saying what you've used the equipment for, that would get you 6 marks. Question 6.2, give one risk of using the equipment in figure 10, where if you go back to the equipment, the most obvious one of a hazard would be the heater, which would be, the risk of using the heater would be burns. Okay, heating stuff up. You could also say broken glass from the beaker, which would give you cuts. Okay, but you've got to say the risk of using it. So the broken glass giving you a cut, the heater giving you a burn. A student did not have a joule meter and calculated the energy transferred by an electric heater. So you probably in school used a voltmeter and an ammeter and a stopwatch to calculate the energy transferred. And joule meters are really expensive. So you can do it using a calculation. Use the physics equation sheet to answer the following questions. Okay, in 2022, they had the equation sheet. So they would just look at their equation sheet and see, well, energy is equal to power times by time. It could also be written power is equal to energy divided by time. Okay, so just read different versions of the equation. The electric heater had a power output of 50 watts. So you know your power is 50. Calculate the time taken for the heating element to transfer 4,750 joules of energy to it. So this time we're finding the energy. So time, if I rearrange my equation here, if I instead of timesing by power, I would divide by power. So time is energy over power. And then I can substitute in what I've got. My energy is 4,750. My power is 50. If I do that on my calculator, 4,750 divided by 50, that gives me a time. And time, we've already given you the units, is in seconds, so 95 seconds. Next part. In a deep fryer, vegetable oil is heated by heating an electric element. Food is then cooked in the hot vegetable oil. The deep fryer contains an electrical component to measure the temperature of the vegetable oil. Figure 11 shows how the resistance of this electrical component changes with temperature. So you can see, as the temperature is increasing, the resistance is decreasing. What electrical component is used to monitor the temperature of vegetable oil? So this is going to be an electrical component that measures temperature or can detect temperature. Well, this would be, there's only one that you should have learned that does this. It's a thermistor. Thermistors respond to temperature, like a thermometer. The symbol of it is a resistor shape because it's a type of resistor, and you've got a flat line, an arrow, and a diagonal line going through it. But you would have to say thermistor. It then says the electrical heating element in the deep fryer automatically switches off when the vegetable oil reaches a certain temperature. Figure 12 shows how the temperature of the vegetable oil changed after the deep fryer was switched on. So you've got the time in minutes going on and the temperature that is going up. Determine the resistance of the electrical component when the electrical heating element automatically switched off. And it's telling me to use figure 11 and figure 12. But I'm after the resistance. Now this graph here, figure 12, hasn't given me resistance. But if I go back to figure 11, this graph has given me resistance. What is the commonality between both graphs? Well, we've got temperature here and we've got temperature here. So we can use that and link the graphs together. So it's saying the deep fryer automatically switches off when the vegetable oil reaches a certain temperature. When can I tell from figure 12 when the fryer has switched off? Well, it must be when the oil has stopped heating. So at this point here when it goes flat. I can then go across, because that would be the temperature at which it turns off. Reading my scale, well that must be gap of 50 and 10 little squares, so each little square is worth 5, 155, 160. So this value here is 160 degrees. If I then go back to my other graph, and I then go to 160 on this axis, so 150 and 160 would be here. I go up to this line of best fit and across. Okay, this is when doing it on an iPad is slightly inaccurate. You would obviously use a ruler. I can see that this result is somewhere between, well, bang in the middle of 200 and 300. So I make it to be about 250. But they do give you a tolerance of anything between 240 and 260. Okay, so it depends on where you draw your line of best fit. But obviously just make sure you use a ruler. So 250 would be your final answer. And then finally, some chips were put in the deep fryer. In the deep fryer, water in the chips underwent a physical change and became steam. Okay, so you've got a physical change, water becoming steam. Why is it a physical change? Well, you should remember that ice can turn into liquid water, that can turn into steam. A physical change is not a chemical reaction. Chemical reactions are permanent and properties change. Physical changes are not permanent because it can be reversed. You should know that your steam can then be cooled down to go back to liquid water and then back to solid ice. So why is this a physical change? Is it because all water can change to steam? Well, in theory, all the water could change to steam, but that's not what makes it a physical change. No chemicals are involved when water changes to steam. Well, that is true again, but it's not what makes it a true physical change. The change from water to steam can be detected visually. Again, yeah, you can generally see it, but that's not what the definition of a physical change is. The water will recover its original properties if the steam is cooled. Now that is what is the key point. It's about the properties being reversible of a solid, a liquid and a gas. And they can be changed from one form to another. So it can be reversed and therefore the properties can be reversed, and that is why it's the bottom one. Right, okay, so that's the end then of this physics paper in 2022. I'll link the Cognito videos below if you need to go back and revise any of the topics. Yeah, but I hope it was useful. Thank you.